And the last few things I want to talk about in this chapter are going to be this field that surrounds charged particles. It's kind of like what we would call an aura. And essentially, if we have any charged particle, then there's going to be some field that surrounds it that's going to let it interact with another charged particle. Now, the way that we kind of draw this is if we have a negatively charged particle, then we're going to say that the field is going to point towards it. And if we had a positively charged particle, then the field is going to point away from it. And it's going to be kind of radial away, kind of the way that I'm drawing right here, pretty much in all directions. And essentially what I'm saying is if I were to take another particle, suppose I were to take another positively charged particle, then I know that it's going to interact with this one right over there. There's going to be some force, and it's going to be a force of repulsion in this case. Similarly, if I were to take a positively charged particle and put this guy right here, I know it's going to interact with this guy right over there. Just like if I had two magnets and I put the norths together, then they're going to repel, or if I put the north to the south, then they're going to attract. There has to be some aura or field surrounding those magnets, and there is one surrounding these electrical charges as well. Essentially, all we're really doing is we're saying that the electrical field is going to be defined as how much force they feel divided by whatever charge we place near them. So kind of in equation form, it's going to look like that, although very often I tend to write this guy in the language of saying the force, and saying the force has got to be equal to the electric field multiplied by whatever charge I put on there. Now, the unit tells you everything. You know, I'm a big person that cares a lot about units. The unit of force is going to be a Newton. The unit of charge is going to be a Coulomb. So anytime you see a Newton per Coulomb, you're going to see an electric, we're going to be talking about an electric field. Let's just do a quick little practice calculation. Suppose I had a charged particle, and I was going to say, for the sake of an argument, that we're going to have a 2 Coulomb charged particle. That's lots and lots and lots of charge, by the way. And it was inside of some electrical field that was equal to, say, 4 newtons per Coulomb. How much force would this charged particle feel? Well, the force is going to be equal to the charge times the electric field. And so that's going to be my 2 Coulomb charge multiplied by my electric field, 4 newtons per Coulomb. And I would have a force of 8 newtons. Again, this electrical field is going to live around any charged particle, and essentially it's going to be the direction of force you would have if you took a positively charged particle and plopped it in there. So kind of as I said, if we had a positively charged particle, the electric field is going to point away from it radially, and if I were to take a charged particle and plop it in right here, we know that it's going to be repulsive force. It's going to go in that direction. This would actually also give us the opposite direction that an electron would go. So if I took an electron and plopped it right here, we know that this is negative and that's positive, so it's going to go in this direction right here. I always tend to remember the positive one myself. Now, I know that electrical field lines are, kind of difficult to imagine. So take, for example, someone's hair. If we were to somehow charge this person, if they were to maybe touch something like a Van de Graaff generator, and there was a whole bunch of electrons that were being generated right here, and they're going to go all through this lady's body, and it's going to go right here. It's going to go to the tips of her hair, and you can kind of see how her hair are going to go radially away. Well, kind of what's happening is these electrons are trying to get as far away from all the other electrons, and they're actually lining up in the same direction as the electric field is going to point. It's going to be kind of radially into or radially away from her head. Now this kind of leads us to our next topic of conversation, which is called electric potential. Another word for this is going to be voltage. And first I want to come back and think about something we know about physical objects. We know that if we were to lift an object up, we were to do some work to it, it's going to gain some potential energy, technically gravitational potential energy. And if we were to go ahead and snip this line right here, then there's nothing holding it back, and this potential energy is all going to transfer into kinetic energy. Now, if we were to, for example, have a negatively charged particle and a positively charged particle, we know that there's going to be an electric field, and that electric field is actually going to point away from the positive and towards the negative. Probably not surprisingly, if I were to cut the line right over here, then these two guys are going to attract and they're going to move towards each other. Here, we're going to have some potential energy, not gravitational potential energy, but now electrical potential energy. And these two guys are going to have some kinetic energy. They're going to fall towards each other, just like these two masses did, only now in an electrical sense. Anytime we're in an electrical field, then we're going to need to do work to go against it, or it can work for us and make objects move together. So picture this scenario right here for a second. Suppose I had a bunch of negative charges and I lined them up down here. And if I had a bunch of positive charges and I lined them up right here, then what's going to happen is I'm going to have a net electrical field that points in the downwards direction. If I were to take for a second a positive charge and I were to say, well, what's going to happen? Well, I know that it's going to feel a force that's related to its charge and the electric field, and it's probably going to be in the downward direction because it's attracted to these negative guys. I have to do some work to lift this guy up in potential. So this may be something like a potential of 10 volts, and this might be a potential of 0 volts. You can kind of think of this being something like 10 meters tall, and this being the ground. It takes work to lift something up. Similarly, once we've gone ahead and we've lifted something up, then what we can do is if we were to release it, then it's going to go down. It's going to go from high potential down into low potential, just like it would go from a higher gravitational potential to a lower gravitational potential. Now, one thing I do want to talk about that's kind of interesting has to do with electric fields inside of conductors. Inside of a conductor, the electric field has got to be 0, and this is just inside of conductors. Now, what's going on with that is if we were to have a conductor, say this guy right here, then the charges are going to slosh around such that the electric field is going to be 0. And if this was a nice, pretty uniform thing, then it's going to distribute kind of like this. If it were to be something that was slightly less uniform, then there's going to be more charge bunched up in the corners, say right here, than in the middle. And you could kind of go in between them. There's going to be more charge bunched up over here than there are over here. Essentially, all of these guys are trying to do the same thing. They're trying to force the electric field to be 0 inside of a conductor, because the electric field must be 0 inside of a conductor. That's kind of the definition of a conductor. Now, this has a couple of implications. First of all, it says that we can actually shield electric fields by putting something inside of a cage, and this is actually called a Faraday cage. And you may have heard that you're safe inside of your car during a lightning storm, and you may have heard the reason for that is because of the tires. Well, it's actually not the tires. If there's enough power for electricity or for lightning to jump from this distance right here, it can certainly make it through this teeny tiny half an inch of rubber that we have. Kind of what's going on is you are electrically shielding, or you are electrically shielded by this metal, by this conductor, and the electrons all rearrange themselves such that the electric field inside are going to be 0, and you're going to be perfectly unharmed. Other implications of this is we can actually shield electric fields, but as of right now, we cannot shield gravitational fields. Other implications of this is you can actually put metal inside of a microwave, but you can't put sharp metal inside of a microwave. If you were to put a spoon inside of a microwave, then the spoon has lots of rounded edges, and the charges are going to slosh around, but they can't really jump off because they don't bunch together. If you were to go ahead and take a fork and you were to put that fork inside of the very same microwave, then you know that it's going to start to spark off the end, and the end, kind of becomes all messed up because of that. What's going on is the charge bunches up on the sharp points just like it does right there, and that's why sharp things spark inside of our microwave, but round things do not. Now, one of the last things I want to finish this chapter off with is a little bit more about potential. I've kind of said that potential is going to be voltage, and I've kind of slipped the word energy in as well a couple of times. It turns out that potential is related to energy, and it's pretty straightforward. Potential is going to be measured in a volt, and a volt is actually going to be related to the unit of energy. It's going to be, which is a joule, and charge. So what we can kind of say at the end of the day is we can say that the electric potential is going to be equal to the electric potential energy divided by the charge. electric potential energy would have joules, coulombs is going to be charge, and this is going to be electrical potential. So this kind of looks like force and electric field, where the electrical field we divided the force by the charge. But all potential really is dividing the energy by the charge, just like we divided the force by the charge. Take this example right here. We could have something that has twice the charge and twice the electric potential, but twice the potential energy, but the same electric potential, so essentially the same voltage. And you could say 3 times and 3 times and make the same exact analogy. Again, please just don't confuse potential and electric potential energy. Electrical potential is going to be voltage, and we can actually have high voltage with low energy. It just depends on how much charge we have. We could also have high voltage with high potential energy, again, just depending on how much charge we have. So something like a balloon that you rubbed up against your hair could have a voltage of 5,000 volts, but very little potential energy because we don't have a whole lot of charge there. As I said, the unit tells you everything. Electric potential energy is in joules. Potential, on the other hand, is going to be measured in volts. Now, one common device that can store electrical potential energy inside of a circuit is actually called a capacitor. And all a capacitor really is going to be two plates that hold some charges that are separated by one another. So if we were to take a metal plate and a metal plate, separate them by some distance, connect this one to the positive side of a battery, connect this one to the negative side of the battery, then obviously this one's going to be positive and this one's going to be negative. And as long as they don't touch, then the charge is going to remain separated. And this thing is going to store some energy, and it's actually going to store that energy inside of the electric field that's going to point from one side to the other. Now, what's going to happen, this just kind of says in text everything that I said on the previous slide, is you connect one side to the positive and it's going to pull electrons away from it. It's going to become positive. The electrons go through the battery and they go to the negative side, so it's going to go to the opposite plate. And technically the plates are going to have equal but opposite charge, and they're going to store energy again and again. They're going to store it in the electrical. The process is going to keep on going until the potential difference, the voltage across the plates, is going to be the same as the potential difference, the voltage across the battery. So if you had a 12-volt battery, then the plates would have 12 volts across them. And it turns out that the more voltage you have, then the more voltage that the capacitor can have, and the more charge that it can store on these two guys. Bear in mind that we are storing energy, and so it requires work to do it, and that would, in effect, drain the battery. A charged capacitor actually can act like a battery, but it can discharge much more rapidly. And discharging a charged capacitor is a very dangerous thing, and never take a microwave apart because there are highly charged capacitors in there. Now, one common example of a device that can store some electrical energy is actually called a Van de Graaff generator, and have some really cool examples of this. And all this guy really is going to be some insulating belt that's going to be driven by a motor. It's going to have some metal points that are going to have some free electrons. They then ride up the support. They hop onto this metal sphere, and since the electric field is always zero, these guys are all going to go to the outside of it. And let's just go ahead and take a quick look at some YouTube videos of what can happen with these guys. Okay, so this is kind of an example of what a Van de Graaff looks like. Again, we have this metal sphere, we have the insulating belt, and what we can do is we can store up lots of negative charges on the outside of it, and these charges can jump, just like lightning can, from one to the other. You can kind of see the jump between the sphere and the other one. It can illuminate things like fluorescent lights, as you can kind of see right here. And if we were to go ahead and put some tin cans on top of it, then what can happen is the electrons can flow through the metal, or in this case pi plates, and they're negatively charged, they repel, and they're going to go flying off, just kind of like that, as each one picks up more and more and more charge. And it can even lift heavy objects, so the gravitational force is not nearly as strong as this creature called the electrical force. You can do this with Rice Krispies or with styrofoam peanuts as well. And if you were to tape some hair to it, then as I said earlier, it's going to get electrons that are here, 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 and here. They all repel each other, and so they're all going to lift each other up, and they're technically also going to point in the direction of electric field lines.